All right, so this is part two of, we're going to be looking at the remainder theorem and the factor theorem. And before we do that, though, let's do this problem number 7. It says determine whether x plus 3 and x minus 1 are factors of what we have here. So basically, if we do synthetic division and we get a remainder of 0, we know that we have something that's a factor. So let's go ahead and try x plus 3 first. So if we're doing synthetic division, go ahead and start setting that up. You should have put negative 3 in the box, and that's how you would set it up. So we bring down the 1, and then we'll multiply, we get negative 3. Add, you get negative 5. Multiply, you get 15. Add, you get 20. Multiply, you get negative 60. When you add, you get negative 64. So in this case, we didn't get a remainder of 0, and so the answer here, it was asking if x plus 3 was a factor. The answer is no. All right, let's try x minus 1. Again, I would encourage you to try it before you watch the video. All right, so you should have, let's see, I forgot to write that on the bottom there. I remember that's our check. If you actually do the division, this is our answer here with our remainder, and I just wrote out the other way that we could write our dividend. All right, so go ahead and let's go ahead and do the x minus 1 division. So you should have set it up like that. Let's go ahead and bring down our 1. So 1 times 1, we're going to get 1. And when we add, we get negative 1. Multiply, we get negative 1. When we add, we get 4. Multiply, we get 4. And when we add, we get 0. So this time we were checking to see if x minus 1 was a factor, and the answer is yes. So basically what we just looked at is going to help us to understand the remainder and the factor theorems, which we'll look at next. But before we do that, I just want to mention what we call the, I forgot to do that part again. So since we got a remainder of 0, notice here we actually found a way to factor this original polynomial. Okay, now we're ready to look at what we call the remainder theorem. Actually, that's the division algorithm. That's not right. Which basically says when dividing a polynomial, we call it p of x, by a divisor d of x, a polynomial q of x is the quotient and a polynomial r of x is the remainder. The quotient must have degree less than that of the dividend p of x. So in other words, when we divide p of x by d of x, we're going to get a lower degree, which is what we've been seeing. The remainder must either be 0 or have degree less than that of the divisor. All right, so let's go ahead and look at the remainder theorem here. If the polynomial f of x is divided by x minus c, then the remainder is f of c. Now this is a pretty simple theorem, but it's probably easier to understand by looking at an example. So we'll use what we just did up above on number 7. So, oh goodness, I keep forgetting some things I have put in. But anyway, let me go ahead and talk about the remainder theorem here. So for example, if we let f of x equal x cubed minus 2x squared plus 5x minus 4, notice that's our polynomial in number 7. And if f of x is divided by x plus 3, which is what we did first up on problem number 7, what this is saying, so in this problem here, f of x is x cubed minus 2x squared plus 5x minus 4, and we're dividing by x plus 3. Now, if we're dividing by x plus 3, what's our c? Well, we have x plus 3, which we could write as x minus negative 3. So if we're trying to figure out what c is here, you can see that c would be negative 3. So what the final part here says that our remainder is f of c. So then the remainder is f of negative 3, since our c here is negative 3. So that's what the remainder theorem is saying. If I divide by x plus 3 here, the remainder is going to equal f of negative 3. Well, let's see why that's true. Well, from up above, and again, I kept doing this part here because I was leading to this point right now. We actually have another way to write f of x. We can write f of x as x plus 3 times x squared minus 5x plus 20 minus 64. So by doing that, now when we find f of negative 3, so I'm just going to go ahead and make a shell, and I'll plug in negative 3. When you do that, this is the key right at the front here. That's 0. You have 0 times 44 minus 64 when you simplify this, which is negative 64, which was our remainder. So this part will always zero out in a situation like this, and that's why f of c is equal to 0. Or, I'm sorry, is equal to our remainder. All right. So what does that mean? Let's go ahead and use the theorem on number 8. It says, use synthetic division and the remainder theorem to find the function value. All right, so we're basically using the theorem we just learned. So in this case, notice your c is negative 2. So basically what the remainder theorem is saying is if we divide this polynomial by x minus c, or in this case that would be x plus 2, you could think of it as x minus negative 2, whatever we get to for a remainder is going to equal f of negative 2. So we're going to go ahead and do synthetic division with negative 2. And let's go ahead and set this up. We're going to drop our 1, multiply, you get negative 2, add, you get negative 8. Multiply, you get 16, add, you get 27. Multiply, you get negative 54, add, you get negative 60. So the remainder here is equal to f of negative 2. All right, so that's how you use the remainder theorem to do a problem like this. Now notice it's requiring you to use synthetic division in the remainder theorem. Isn't there another way to find f of negative 2 though? Couldn't you just plug it into the function? So even when you're asked to do a problem this way, you could certainly check it if you feel like you want to by just plugging it into the function. All right, let's move on to number 9. So I'd encourage you to try number 9 and then watch the video. All right, on number 9, so in this case, our c is 3. And so basically, if you divide this polynomial h of x by x minus 3, or x minus c, whatever you get for a remainder is going to equal h of 3. Now notice here, we're missing some of our powers of x. So you're going to need to put in 2 zeros. So you put 3 in the box and set it up just like that. Let's go ahead and bring down the 2, and then we'll do our multiply add here. So 2 times 3 is 6. When we add, we get 6. 6 times 3 is 18. When we add, we get 8. 8 times 3 is 24. When we add, we get 5. 5 times 3 is 15. When we add, we get 15. And 15 times 3 is 45. And we get negative 5. So that means h of 3 is negative 5. Now I did write f, but it should be h. Let me just fix that real quick. That's an easy fix. Let's see. All All right. On the factor theorem, the factor theorem is really the one that we care about the most. The remainder theorem just kind of leads into the factor theorem. So here it says x minus c is a factor of the polynomial f of x if and only if f of c equals 0. Well, when we did number 7, we were kind of already seeing that when we get a remainder of 0, that tells us we've factored the original polynomial, or dividend. So that's really what this theorem is saying. A remainder of 0 means you've got it factored. So let's use our example up above. We said x minus 1 is a factor of, well, we actually found that x minus 1 is a factor of f of x here. Again, this is that same polynomial from number 7 that we did in the previous slide. So if x minus 1 is a factor, and we actually did our work and we found, let's see, so in this case we're dividing by x minus 1. So x minus c, our c value here is 1. So when we did the synthetic division, we got a remainder of 0, and we were able to rewrite our function, and that's what we're going to do. We're going to rewrite f of x in factored form. Our answer on number 7, we got x squared minus x plus 4. So when we did the division by x minus 1, we got an answer of x squared minus x plus 4. It enables us to write the function f in factored form. Now let's go ahead and find f of c. In this case, we said c was 1. So again, I'll set up a shell and we'll plug in 1. And again, notice what's happening right here. 1 minus 1, we're going to get 0. It really doesn't matter what the other part is. And so f of c does give you 0. And so again, we kind of already figured this out. Now we're going to start using it. We call it the factor theorem. All right, so when you see a problem like number 10, it says, is x minus 2 a factor of the polynomial x squared minus 5x plus 6? Well, we just need to do synthetic division with 2. So let's go ahead and do that. If we get a remainder of 0, then we know that it is a factor. So notice you do get 0 here, and so the answer is yes. Now keep in mind, these kinds of problems can be asked a couple of ways. We could say, is 2 a 0 of the function f of x equals x squared minus 5x plus 6? Because we know that zeros and factors go hand in hand. So look at number 11. It says, is x equal negative 5 a 0 of f of x equals x cubed plus 2x squared minus 6? Well, if x equals negative 5 is a 0, then we know that, oh, I forgot to do that part again. That was number 10. We could write it in factored form. So here, if x equals negative 5 is a 0, then we know x plus 5 is a factor. That was something we learned in the previous lesson. I guess that would be section 4.2. So let's go ahead and do division. Notice you're going to need to put a 0 in for the x term. So we have you should set it up like that. Let's drop our 1. You multiply, you get negative 5. Add, you get negative 3. Okay, multiply, you get 15. Add, you get 15. Multiply, you get negative 75. Add, you get negative 81. So we didn't get a remainder of 0, so this is not a factor. X plus 5 is not, which means, excuse me, x equals negative 5 is not a 0. So the answer would be no here. All right, let's move on to the next slide. It says factor f of x equals 6x cubed plus 19x squared plus 2x minus 3 completely then solve the equation f of x equals 0. Now, notice here, this cannot be factored by grouping. And so we've got a problem here. How do we find the first 0? Now, one thing that you can do is you could just start, if you wanted to see if x plus 1 was a divisor or a factor, you do synthetic division and see if you get a remainder of 0. You could repeat that with several different numbers. I'm going to be allowing you to use your calculator to find the first 0. So let me show you how we're going to do that. So first of all, you should put y equals this function into your calculator. If you forgot how to do that, I'll make a little video to remind you. But when you put it into your calculator and you use the table function, you should be able to find a 0, and I'll let you use 1, 0 from the calculator. So when you do that graph, you'll find that x equals -3 is a 0. Remember, if you find an x-intercept, that tells you a 0. So you'll find an x-intercept at -3. So we got that off the calculator. So now we can confirm that it's a 0. And again, once you've got that first 0 off the calculator, that's it. You can't use the calculator for anything else. We're going to go ahead and confirm that -3 is a 0. So let's drop our 6, multiply, you get -18, add, you get 1. Multiply, you get -3, add, you get -1. Multiply, you get 3. When you add, you get 0. So our answer here is 6x squared plus x minus 1. But the value of our answer is we can factor the original polynomial as x plus 3 times 6x squared plus x minus 1. Now at this point, we're hoping that we can factor this other polynomial, 6x squared plus x minus 1. In fact, it's a trinomial, so we'd try the AC method. We need two numbers that multiply to -6. Remember, that's our AC, 6 times -1, and add up to the coefficient of the middle term, which would be 1. So 2 and -2 and 3 are what's going to work here. So we'll bring down our 6x squared. We'll split our middle term x into -2x plus 3x using the numbers we just found, and we'll bring down our -1, and then we'll factor by grouping. So in the first two terms, we can factor out a 2x. Let's see, 2x times 3x gives you the 6x squared, and then 2x times a -1 will give you the -2x. And when we factor here, we're expecting a 3x minus 1. Remember, the parentheses should always have the same binomial inside. And so that must be a plus 1 in between. So we get 3x minus 1, our common factor for those two terms, times 2x plus 1. So we can now factor f as x plus 3 times 3x minus 1 times 2x plus 1. Now we're supposed to set this equal to 0 and solve for x. Basically, we're finding zeros. Excuse me. So we already knew x, so I'll set them all equal to 0, but we already knew x equals -3. We had got that off the calculator. When you solve these other two equations, you'll get your other zeros. So we'll add 1 there to both sides. We get 3x is 1. So we're going to get 1/3. And then here we're going to want to subtract 1 on both sides and divide by 2, so you get -1/2. So those are our zeros, -3, 1/3, and -1/2. Now you might have been able to figure those out just from getting them off the calculator, but again, I want to remind you, you can get the first 0 off the calculator, and then after that you're going to have to show all the work to get the other zeros. And normally what it comes down to is you break the polynomial down until you get something quadratic, because we can solve quadratic equations if we're looking for zeros. And we can also factor often when we have a trinomial that's quadratic. Okay, number 13, it says sketch the graph. Use synthetic division and the remainder theorem to find the zeros. Well, if you're going to sketch a graph, we learned back in 4.2 that you need to first look at end behavior. So notice our leading term is x cubed. So our degree is odd here, or 3. So we're odd, and we're positive because this is a 1 out front, positive number. And so hopefully you remember that little chart we looked at. Our end behavior is going to look like this. It has the same end behavior as y equals x cubed. I call that the John Travolta end behavior. And let's see. So next, from the calculator, you could find a 0, and the easiest one would be 1. You could actually see them all, but I chose 1. I usually try to keep it simple and positive. So again, once you get that first 0 off your calculator, you need to confirm that it is a 0. Notice we don't have an x squared term, so you'll need to put a 0 in for the x squared column. So when you set it up for synthetic division, it'll look like that. We'll drop our 1, multiply, you get 1, add, you get 1. Multiply, you get 1, add, you get -6. Multiply, you get -6. When you add, you get 0. And again, we're expecting 0 because we know that this is a factor. We know that 1 is a 0. Or x minus 1 is a factor. All right, so now we can write f of x as x minus 1, which is what we were dividing by, times the answer we just got here, x squared plus x minus 6. Now again, remember, this should always be your constant. So then again, I'm hoping I can factor this. I need two numbers that multiply to -6 and add to 1. Since this is a 1x squared, we can take the shortcut here. We don't have to split our b term. The numbers that work are -2 and 3. So we get x minus 1 times x minus 2 times x plus 3. So our zeros are 1, 2, and -3. Now again, you could have just gotten those off the calculator, but all the work that we just did here is confirming that you understand the process, the algebraic part of getting the answers. It's not acceptable to just say, hey, that's what I found on the calculator. All right. And sometimes the calculator kind of just gets you started. In this case, we had really nice zeros, but often the zeros won't be so nice. Okay, so let's move on. So next we'll do a Zmb chart. Remember, Z is for 0, M is for the multiplicity of the 0, and B is for the behavior of the graph at the corresponding intercept where we have a 0. So our zeros are 1, 2, and -3. Notice all of our powers, these are all to the first power. Or another way to say that is there's a single factor for each of the factors. And so the multiplicity is 1. And so we know that at each of these zeros, or the x-intercepts, the behavior is the graph's going to cross. So now we're ready to graph. So first of all, you put in your x-intercepts. Those will be at 1, 2, and -3. Next, we put in our end behavior, which on the left we know it falls, and on the right it rises. And then we'll go from left to right, and each time we're going to cross here. So when we get to -3, we cross. And then we know eventually we have to come back down, and we'll go through the next x-intercept. Now we don't really know how high we're going to go, although we could find f of -1 or -2. Or even f of 0, and you could get some points. But we're just going to do a rough sketch here. So we'll pass through or cross again. And again, we don't know how far we're going to go down, but eventually we have to come back up and cross again. And notice that matches our behavior there. All right, so the video for this lesson is done. I am going to have one more video just where I do a couple problems where the numbers aren't so nice. And so if you want to look at those examples, you can.